Now, we have polynomials, the definition of a polynomial. It's an expression with a variable x raised to integer powers. Now, what is an integer? It's a whole number. In this case, we're looking at positive whole numbers. So 1, 3, 600, they're all integer numbers, positive integer numbers. And when we raise x to that power, we get what's called a polynomial. In methods 3 and 4, you're going to have to know exactly how to sketch these functions, how to solve for x when the function equals 0, factorize these functions, and find rules given a particular graph or given some information about a particular polynomial. So you need to get very, very familiar with the shape of the graphs of the polynomial, as well as just some general properties of polynomials. And we're going to be exploring that throughout this lecture. Now note that every polynomial has what's called a degree. This is the highest power present in the polynomial. So if we look at these three examples here, 32x to the 7 plus x to the 5 minus x, the degree here would be 7, because that's the highest power that we have present. In the second example, we can see the highest power is 2, so the degree of this polynomial is 2. And in this case, the highest power is actually 0. If you can imagine an x to the 0 tacked onto this root 3, that would still technically be a polynomial. So in this case, it's a polynomial of degree 0. Okay, so yeah, value of the highest power present. Now, in terms of sketching polynomials and solving for polynomials when they're equal to 0, we're going to first look at quadratics, and then we'll look at cubics and high polynomials after that. So with quadratics, yeah, there's two kinds of questions that you're going to generally get, and it's going to be either a quadratic that's equal to 0 and you have to solve for x, or you're going to have a question that asks you to sketch a quadratic, which also involves solving for the quadratic when it's equal to 0, because that's how you find the x-intercept of the quadratic. Of course, we'll get a little bit into that later. But this table gives us the different forms of quadratics and also shows us what information we can take away from it, which is especially important when we're sketching the question. So I've labeled that row with a little star here. With the turning point form, it looks like this. And the info that it gives us at face value, just looking at the equation, it'll give us the turning point, which is at the coordinates h and k. So if this was y equals a times x minus 3 squared plus 4, then our turning point is 3 and 4. Factorized form looks a bit like this. The face value information that it gives us is the x-intercepts, b and c. And then expanded form gives us the y-intercept, which is the value c. We'll look a little bit more into this key info that it gives us at face value in the next slide. One thing I also want to touch on though is when we set each of these expressions equal to 0, then there's a particular method that we have to use to solve for x. In the turning point form's case, we rearrange for x. In factorized form, we have to use the null factor theorem. So each one of these linear factors, either x minus b or x minus c, is equal to 0 by the null factor theorem. And in expanded form, we can either use the quadratic formula, or we can convert this expanded form to factorized form or to turning point form, and then use these methods that I've described here. Okay, so we've first got turning point form and factorized form. In terms of just looking a little bit into more detail on that face value key info that each of these forms gives us. So the turning point form tells us where the turning point is. So graphically, it would look something like this. That's the turning point right there, h and k. And yeah, it says here that if a is greater than 0, then it's going to be an upright parabola, so like a smiley face. But if a is less than 0, then it's going to be an inverted parabola, so it's going to go down like this, like a sad face. We'll look a little bit more into that when we look at transformations, but generally with quadratics, those are just some key things you want to watch out for. It makes it easier for you to visualize how the parabola is going to look. Um, we also have factorized form. So again, it tells us the x-axis intercept. So in this case, we have an intercept at B here, and then an intercept at C here. Okay, so that's for all for quadratics. Now we've got higher polynomials. So this table here, it describes the forms of cubics, polynomials of degree 3, but generally these forms will also apply for higher polynomials like quartics, even quintics, but you won't have to study those. Those are outside the scope of study design. Just cubics and quartics you'll have to worry about. Now, something you'll notice is that this table is very similar to that table that we saw a couple slides ago, this one here, to do with quadratics. Which is good because it means that there's a lot of information that crosses over from quadratics to polynomials. The only thing that you should note though is when we're solving for x with the expanded form, when it comes to cubics and quartics, we're no longer just using the quadratic formula. We instead have to factorize via long division to get to factorized form. And the way we do that is using the rational root theorem and then the factor theorem. And then from there, we can apply the null factor theorem to solve for x when this cubic is equal to 0. Another thing I want you guys to notice is with the inflection point form, this is now telling us where the inflection point is at face value. So this is a little bit different from a turning point, and you guys might have a bit of experience with this already from your 1-2 study, but we'll go into it a little bit now. Please make sure to ask any questions if you've got any along the way. All right, so let's talk a bit more about the additional features of a cubic that you have to watch out for. For the most part, it's the same stuff, right? So we're talking about x-intercepts, y-intercepts, turning points. One thing you actually have to start worrying about with cubics as well, though, is what we call stationary inflection points. So this is where, if you look at this diagram here, it's where the graph approaches a point and then begins to kind of flatten out. Eventually it reaches a point where it has 0 gradient. So that's right there in the center. It's running flat, parallel to the x-axis. But then immediately starts heading back in the same direction it came from. So this is what's called a stationary point of inflection. And something you want to make sure you don't do is don't confuse it with a point of inflection. Now, points of inflection in general are points of the graph where the steepness of the graph reaches a maximum or minimum. So you can see here, if we look at this graph, the steepness of the graph is decreasing, decreasing. Eventually it reaches 0, so it's reached a minimum, and then it goes back up. So that's a point of inflection. This is also a point of inflection right here, though, because we can see here at this point, the steepness of the graph is going down, down. It's getting more and more negative. Eventually it reaches a point here where the gradient is at its greatest negative value. I know there's a bit of a double negative there, but it reaches its greatest negative value, and then it starts the gradient starts increasing towards positive values again, and eventually the graph starts going up again. So this right here is a point of inflection. For those of you learning Spec Maths, you're going to need to know these, but in methods, you just need to know that, you just need to know what a stationary point of inflection is. And it's the case where an inflection point happens to have a gradient of 0. That is, the inflection point is flat. So you can see here, this is a stationary point of inflection because the gradient is flat. Well, it's 0 here. That's one thing you want to watch out for, stationary points of inflection. The other thing you want to be familiar with is the general shape of a cubic. You can see here, it's nothing like a quadratic, right? Whereas quadratics, it's just going down, then going up, and going up and then going down. Cubics have a particular characteristic shape. It's a mountain. You can see a mountain there, and then a valley. Now this doesn't always apply. Sometimes you might have just a bit of a wiggle like this. It's not really a mountain and a valley. But just remember that it can have any one of these forms. In general, just remembering that it's a mountain than a valley will help you out a lot when it comes to tackling questions involving cubics. Okay, now moving on to quartics. It's a quadratic but with a squarer base, and there's not much more that can be said there. You can see it looks like a quadratic. It comes down and then it goes back up, but you can see how it's a bit flatter at the bottom. So it comes down and then it flattens out and then it goes back up. Now, the thing is, it can still have turning points. Well, I mean, you can see in this diagram here, it has a turning point, but it can also have stationary points of inflection. Looking down at this graph here, we have a stationary point of inflection right here. It goes up to that point and then gets flat and then it keeps going the same way. You can also have situations where you have three different turning points, in which case you get, like here, you have an upside down W. You might have a not upside down W, just a normal W looking shape. So in general, just remembering you can have either U's or W's for positive quartics. So that's equations with the greatest power being 4 and no negative sign out front in this x4 term, x to the 4 term. This is going to take the shape of a U or a W. Okay, so in terms of identifying when a stationary point of inflection occurs, just by being given the equation of a polynomial, there's actually going to be some very clear signs that, like if a polynomial has an inflection point, it's going to show up in the factorized form of the polynomial. So if we have a particular polynomial, say we have a quartic, and we convert it to factorized form, if the factor has this shape, or has this form, so x minus a, then the graph is going to cut through the x-axis at the point A. If we have that factor raised to the power of 2, so it's a quadratic factor now, then the graph is going to come down and approach A at the x-axis. It's going to touch A and then it's going to come back the same way it came from. So it's kind of like a quadratic. Now, if the factor is raised to the third power, that's when we get a stationary point of inflection. And these are like I said before, they're the only kinds of inflection points you're going to have to worry about. The stationary kind of inflection points. So that's that there. All right, so just as a little bit of an exercise, what I'm going to do is I'm going to help you guys figure out how to sketch this cubic right here. So we have y equals x to the 3 minus 4x. The first thing we want to do is identify what form this polynomial is in. Now we don't have any brackets, so it's definitely not factorized form. What else? It's not stationary point form, because that's the form where we have some kind of linear factor raised to the third power. So this is going to be expanded form. The phase value info we can get from expanded form is the y-intercept, as we saw in previous slides. In this case, the y-intercept is going to be 0, because it's given by the constant term out here, which is just 0. So we can write here y-intercept equals 0. The x-intercept, what we do to solve this is set this expression equal to 0. So we have 0 equals x cubed minus 4x. And then we need to think about how we can factor it. So with a polynomial in expanded form, remember with cubics we have to convert it to factorized form and then apply the null factor theorem. So that's what we're going to do here. In this case, we don't have to resort to the rational root theorem and the factor theorem, but we'll go into that a little bit later. So in this case, we can see a common factor between these two terms is x, so we can factor that out. We'll write x out the front here, and then here goes x squared, because x squared minus x is x cubed. And then here we write minus 4, because negative 4 times x will give us negative 4x. What we can then do is use our difference of two squares, and reduce this further into its linear factors. So x squared minus 4, that's the same as x squared minus 2 squared. So that means our factors will be x plus 2 and x minus 2. Then we can apply the null factor theorem. So this tells us that x, well, the first x value we have is negative 2, because we have this factor x plus 2. Or we have x equal to 0, or we have x equal to 2. The x equals negative 2 comes from this factor, the x equals 0 comes from this factor, and the x equals 2 comes from this factor. That's the x-intercepts. Now the turning points, again, you might have a little bit of practice with this from your 1-2 study, in which case this will be useful to you just as a quick reminder. With the turning points, remember, we're just looking for where the derivative is equal to 0. So we know that the derivative is going to be, we have x cubed, so the derivative of that is 3x squared. You bring the power down and then subtract 1 from the power. And then the derivative of negative 4x is minus 4. Then we can just say at the turning points, dy dx equals 0. Therefore, 3x squared minus 4 equals 0. And then we can state that x squared is equal to 4 over 3. So x is equal to, what is that? Plus or minus square root of 4 over 3. Just doing a little bit of simplification. This is going to be plus or minus 2 over root 3, so it'll be 2 root 3 over 3. Okay, yeah, that looks right. Okay. Yeah, okay, cool. So we've got our x values here. We can then just plug those into our equation to get the y values. So when x equals 2 root 3, I feel like I've done something wrong here. 2 over root 3. No, that's correct. Okay. 2 root 3 over 3. Y is going to equal 2 root 3 over 3 cubed minus 4 2 root 3 over root 3. Running out of space here, but you would go on to simplify that, and eventually you would state your turning points and their coordinates. And then this will be useful in sketching the graph. So it's going to look something like this here. Now, we're going to now move on to some formulas that you're going to find useful when it comes to converting polynomials from expanded form to factorized form. So yeah, we're going to look at these formulas, and then we're going to go on to learn how to use the rational root theorem and the factor theorem to factorize some other cubics in expanded form to factorized form. I'm getting caught up on my own words there. Okay, so these formulas are very useful. Please memorize them, because whenever you find an opportunity to use them in your working, they're going to save you a lot of time. So for cubics, you have x cubed minus a cubed. That can be factorized into x minus a times x squared plus ax plus a squared. So that is, let me get my pen back. There we go, my mouse back, sorry. You can see we've got x minus a, so the linear factor is also x minus a. And then because we put a minus here, we're going to put a plus sign in the quadratic factor here. So x squared plus ax. And that's kind of vice versa for x cubed plus a cubed. We can factorize that into x plus a and x squared minus ax plus a squared. Now, for any polynomial, if you're looking to expand it, then you can use Pascal's triangle. What I mean here is if we look at this formula, x plus a squared, this is the perfect square formula. You get x squared plus 2ax plus a squared. But how do we know what these coefficients are? In this case, 1, 2, and 1. We just look at the third row of Pascal's triangle. So 1, 2, 1, we see it there. For cubics, the expansion formula is x cubed plus 3a squared x plus 3ax squared plus a cubed. And the way I got those coefficients is looking at the fourth row. So whatever power you're raising a linear factor to, look at the look at the row number on Pascal's triangle, but add 1 to it. You're looking at that row. And for those of you that don't know, Pascal's triangle is just formed by adding up the two numbers above it to get the current number. So in this case, in the case of 2 here, we do 1 plus 1, and that gives us the middle number here, which is 2. In the case of 6 plus 4, we have 10. So on and so forth. That pattern just continues down the line. So either you can use that, or you can just remember the cubic, quartic, and quadratic expansion formulas. So this is the quadratic one here. Just remember the cubic and quartic equivalents. Okay.